My name is Jacob Wessel. Me and my colleague Alexandra will give you some insights today in what we understand under digitalization in the battery cell production. Please bear with me. I want to start with a short introduction of the Battery Lab Factory Braunschweig, just because we are from the Battery Lab Factory Braunschweig, and we would like to introduce our understanding what we do there in this area. After this, we will jump right into the topic and discuss and give you some hints and some insights into what we understand behind the terms, and give you maybe some ideas what you can work and how you can improve, of course, your digitalization in your facilities. Please use the chat at any time. Write questions if you have any. As Dimitra mentioned, we will try to pick them up during the discussion parts. But please also try to be not shy, unmute yourself, turn on the video and ask questions directly, so that we can start and jump right into a fruitful discussion, because I think this is the main part of what we are interested in, hearing from you, discussing with you, and maybe talking about more specific problems, since our idea here in this presentation is just to give you an overview, because 2 hours is not a lot talking about digitalization, so it's basically an overview you will see. Perfect. So first, let us look at the agenda for today. I've mentioned before we want to start first with an introduction of the Battery Lab Factory Braunschweig. After this, I will give you a short motivation and introduce the first and for us most important term, the Cyber Physical Production System, CPPS in our words, most likely. In agenda item 3 and 4, we will introduce the different elements of a cyber physical production system, and give you some insights in what to take care of when looking towards digitalization by the means of a cyber physical production system. And I will finish my talk with a short summary and outlook, or our talk with a short summary and outlook, and leave some more room, hopefully, for some discussions. So let us start with the introduction of the Battery Lab Factory Braunschweig. The Battery Lab Factory Braunschweig is a research facility of the TU Braunschweig. We facilitate research in production technologies, looking at lithium-ion battery cells mostly, but also on other cell technologies such as all solid state. We run a full pilot line, which enables us to understand the process itself and the interrelations along the different process steps, because the production environment or production process of lithium-ion battery cells is quite complex. What we understand behind pilot lines or pilot production facilities is quite important. I think those terms are not new for you, but I wanted to bring you some definitions in our understanding today that we all talk about the same topics. When you normally start at looking at cell technologies, you normally look on a laboratory scale. So you have different stations where you build a cell, doing research on different parts along the production process. And this laboratory scale is mainly for testing and evaluating new principles as a proof of concepts. When you, of course, take those proof of concepts, those materials and those insights you gain from laboratory scale and want to scale them up, this is normally the part where pilot lines of battery cell production step in and try to help you there. And this is also what we do. We try to learn about different challenges along the battery cell production process by introducing new, novel production technologies. A good example in recent past could be the extrusion process for continuous dispersing. But we also want to learn about scale-up effects. So how to scale up a single process, how to scale up a technology, a new material, to help industry to better understand what they need to do and need to look for when wanting to scale up their industry up to maybe mass production. One important part, especially for digitalization, is of course the generation of data. Data is the most important thing when looking towards research and digitalization and production facilities, because we need a lot of data to gain insights into the process. And this is the great thing about pilot lines. We are able to gather as many data as we want and use that for our specific use cases. Normally, as we're talking about digitalization today, the aim behind that is understanding the process structure performance relationships. You will hear this term quite often today, I think, to better understand the complexity behind single processes, the single products along the production process, and try to improve certain steps here. Now we will jump quickly into the timeline of the Battery Lab Factory. I don't want to give you like deep insights of the Battery Lab Factory Braunschweig, since I think most of you are already familiar with the Battery Lab Factory Braunschweig, but just a short overview. You will get the slides in the end of the presentation anyway, so you can, if you have questions, of course, use that as like a reading material, but also try, or if you want to get in touch with us, talk to us. We started in 2007 with our first activities with industry, looking more closely at battery production. The first process we looked closely at was the calendaring process, understanding the interrelations of the calendaring within the production of single cells. In 2014, we started with the official building of the Battery Lab Factory Braunschweig, which was funded through an EFRE project, which we got in 2011. So now we have a in-place facility with different dry rooms and a large facility for testing and evaluating the production process. The Battery Lab Factory is part of the ProCell cluster, which is a German excellence cluster, German competence cluster, looking on the production process of lithium-ion battery cells since 2016, and also Professor Quade, who is a professor at the Battery Lab Factory Braunschweig and the IPAD, is the head of the ProCell cluster. We successfully introduced the International Battery Production Conference in 2018. This conference will also come up in 2 weeks. So we're looking really forward to seeing some of you, hopefully there, and discussing on that platform with you about recent advances in lithium-ion battery cell production. In recent past, we scaled up a bit more with different clusters, competencies clusters funded by the German government, such as the Greenbat cluster, which is looking at how to produce a green battery, or looking more towards sustainable and circular production of battery technologies in the future. But also, as you all know, this is why we're here today, we are member and president of the LiPLANET cluster in the person of course, Arno Quade, Professor Quade. After this, let us have a short look at our research and industry network. Really just a short look. The Battery Lab Factory is a research facility that sums up a lot of different institutes of the TU Braunschweig and other institutes as well, in Clausthal-Zellerfeld and also Hannover, just to mention a few of those. But apart from the Battery Lab Factory, we have many more research facilities that work together with us, that help us to better understand and better work around the topic of battery cell production. Apart from that, we are part of a lot of core partners, which is, again, LiPLANET part of, but also the CARLab cluster, which is a competence cluster of lithium-ion batteries. And apart from those, we have an extended network, which goes more towards like research networks, such as the SERP community. I think a lot of you are also part of that community, but also the BDP, which is similar to the SERP community, but just in Germany. Our approach at the Battery Lab Factory Braunschweig is to facilitate knowledge-based circular battery cell production by looking at the entire process in a circular way. So we look at all the single processes, starting with the primary material processing and material synthesis, but also the production steps, including the electrode production and the cell assembly, and the testing and use of the battery cell, and then again trying to look at the recycling process and how can we use the material of used battery cells and reintroduce those maybe into the production environment. We focus mainly on new production processes, so we do not look in detail on new cell chemistry, cell technologies. We do that, of course, but the main focus of the Battery Lab Factory is on the production processes. And here, trying to improve those by the means of new technologies. So something like inline process sensors are, of course, important, understanding a bit better what actually happens inside the process. The Battery Lab Factory Braunschweig has different working groups, which you can see here. Again, those working groups are aligned to facilitate a sustainable circular production of battery cells. We today want to mainly talk about the two groups you can see here on the top: closed loop supply chain management and circular factory design, and computational engineering and digital twin. So those terms are quite familiar, of course, for you, but also the entire production process, you know. Today we are here from those two groups. I've touched on that earlier today, just a few minutes ago, but I want to explain it a bit more in detail why it's so important. So the battery production system itself is quite complex, as we all know. It has many different challenges, many different products and processes, and all those processes and products are interlinked and have interdependencies along the way, influencing the final product. What is complicated to explain and difficult to explain is the interrelation between a process and the final received property of the battery cell. So how does a single process influence the final property of a cell, and that by the means, for example, here the discharge capacity. There's no essential understanding on that yet, and we try to build that way by going the way of process to structure and structure to property. We understand quite well how a single process influences a single product, an intermediate product in the production chain itself. So how does the mixing influence the structure of the slurry that is produced? We know that, and we can describe quite well the properties of that single product, so the slurry in this case. And what we do by the means of experiments, simulation or modeling, and also data-driven predictions is to draw a link between the structures that you perceive along the production chain and the final property of the single cell. You can do that by either doing a process chain simulation, linking different simulations together, and hereby gaining understanding, gaining better knowledge, how the final product will maybe perform when looking at like the first intermediate product in the production chain. You can also do that by data-driven approaches, and hereby trying to enable data mining, predicting qualities, and learning with the data that you perceived from previous production facilities. So you will see how we embedded this process with our facility, how we go from process to structure and from structure to property in the next couple of hours. I've mentioned that before. Today we are here mainly focusing on computational engineering and digital twin. And what we aim here for is to further or foster a comprehensive understanding about data acquisition, data storage, and how to enable by those two important parts a cyber-physical production system, and hereby bringing knowledge back to the production facility by the means of gathered data and analyzing and understanding this data that you gathered. After this introduction, I want to continue with the motivation and want to introduce the most important term, which I've touched on previously, the cyber-physical production system. When talking about digitalization, you immediately think about Industry 4.0, because those two terms are quite closely linked together. Digitalization and Industry 4.0 are not the same. This is quite important to say, but digitalization comes normally before the part of Industry 4.0. Digitalization is a term that has been around for a couple of years, starting with the third industrial revolution. I will touch on that later. And Industry 4.0 takes the means of digitalization and scales them up, further uses them to better understand, again, the insights of your production facility by the means of enabling cyber-physical production system, digital twins, whatever you can think about. Industry 4.0 describes the fourth industrial revolution. Some people call it a revolution, some people call it the evolution. I don't want to touch on that today. I just want to talk about where it comes from. We started with the first industrial revolution, as you all know, by the means of introducing mechanical production plants powered by hydro or steam power, which scaled up the productivity of a production environment, which was previously done by mainly manual work. The second industrial revolution introduced the term of mass production, with the first production chains, which introduced division of labor, and hereby increasing again the efficiency of production systems by dividing tasks to specific workers, and workers perform this task and increasing their activity efficiency. The third industrial revolution is closely linked to the introduction of IT services or IT technologies within the production environment, and hereby increasing the automation within the production. So this is normally where you hear about robotics, where first robotics was introduced into the production facilities, but also terms such as a PLC, so a programmable logic controller, was introduced, and they were getting more cheaper and more quickly introduced into the production environment. Within the fourth industrial revolution or evolution, those technologies are further used. So the availability of IT technologies enabled us to better understand what is actually happening within the production facilities, and the new technologies that were developed around the term IT technologies, so something like Internet of Things, connected devices, they were all introduced within the fourth industrial revolution, enabling us to look inside the production, gather data, understand that data, analyzing that data, and then learning from that data. And all those terms come closely with the cyber-physical production system. You can call, of course, the cyber-physical production system a digital twin. In our understanding at our institute at the Battery Lab Factory Braunschweig, we normally use the term cyber-physical or cyber-physical production system. But if it's easier for you, think about the digital twin. It's basically similar or basically the same. It just is a different word for basically describing the same approach and the same topic in our understanding, of course. The goals of the Industry 4.0 around the cyber-physical production system, again, is to increase the flexibility and the efficiency in production environments. The vision and the key drivers, which you can see here on these slides, are, as mentioned before, the maximization of flexibility. So by the introduction of more products and more in individual products, which are customized, we need something like a self-organizing production system. And this is enabled through Industry 4.0 and the methods behind that and the technologies behind that. With Industry 4.0, you're able to reduce the lead time by avoiding discontinuities. So like scaling up your production, fastening up your production, better knowing what happens if you fasten up your production. And also, which is quite important because we are from the Institute of Sustainable Production, you can increase the energy and resource efficiency by the means of digitalization and Industry 4.0, and using those methods to increase the efficiency, using less energy, using less material. In specific for the cell production, it's quite important, reducing scrap, and hereby reducing the impact, the environmental impact of the single production system or the product on the environment. So we have talked about the cyber-physical production system before. Now I want to introduce the different elements, how we understand a cyber-physical production system, and what we normally see behind it. So in general, the cyber-physical production system is divided into 4 elements, starting with the physical world, second element, the data acquisition and management, third, the cyber world, and fourth, the decision support and control. What we understand behind the physical world is basically the business understanding. So defining your process, explaining your process, knowing about the process, what you actually physically see. So in the case, it can be a factory, it can be a single process, it can be a product. This physical world is connected to the data acquisition by the means of different technologies. We will talk about industry communication protocols later on, so OPC UA, Profinet, Modbus. There are many more. We will give an example later on. But also what we have is a lot of manual data, or just data that you just can want to have within your databases to later use for different approaches. The data acquisition is also a topic we will talk about later on. There are different parts and different elements within that element. It's the data acquisition, of course, it's the data management, and it's also the data provision. So how can we provide data to the next element, which is the cyber world. The cyber world can be understood as the digital shadow of the physical world. So we try to build a model or try to rebuild the understanding of the physical world within simulations, within data-driven approaches, within just data analytics, whatever you can think about. That is the cyber world. And the cyber world uses the data, so it's connect through with the physical world through the data acquisition, uses the data and try to make sense of the data, giving back results or giving back ideas how to improve or how to just getting insights of your production. We then have the fourth element, which is basically the feedback loop towards the physical world, which is quite important because the cyber world itself cannot give you improvements or will not give you improvements by just linking that to the physical world. You need the fourth element, which is the decision support and control system, where you use the insights from the cyber world to enable either recommendations, visualizations, or approaches like that. We will talk about that later on again and giving you some ideas what you can think about here. Before I will hand over to Alexandra, which is also quite important here within the cyber physical system, is that the human needs always will stay in the loop. So we don't have a fully automated cycle here. We have always the human in the loop. The human as a controller, as a decision supporter, as the last person inside the loop that makes the final decision. You can, of course, go towards like automating the process without the human in the loop, but it's quite dangerous. So that's why we try to, at least with a visualization, try to keep the human in the loop. So this is just like briefly what I've explained. Data acquisition normally comes with sensors, cables, network infrastructure, servers, whatever you need to gather data, save data, and provide data to the next world. The cyber world includes computers, servers, again, software to analyze, to make sense of the data, and visualizations can be used for the decision support, but also controllers, actors, many more different technologies. So this is the understanding what we will talk about today. We will try to use those four elements, the physical world, the data acquisition world, the cyber world, and the decision support world, and give you some insights into each element and try to deliver some ideas what you can use and how you can use those elements to digitalize your facility or go towards improving your specific use case. Before we hand over some application fields again for the cyber physical production system. Just for your understanding, you can use it in many different ways. Today, we will talk a bit more closely about the example of quality management. So how can cyber physical production system enable a better quality management, reducing scrap in battery cell manufacturing, or how to just give insights into if the process is running well or not well. Energy and resource efficiency is quite important, also using visualizations, using data that is gathered, making logic of the data, showing the worker how the energy was consumed during the production, increasing transparency is quite important, but also factory planning is quite important. All of those are important, but factory planning comes also with the cyber physical production system. By knowing better about your system, you can better improve planning your factory, either by adapting your facility that you have or using the knowledge that you gathered for new planning cycles along that field. With that, we're done with the first part. I will now hand over to my colleague Alexandra for the agenda item 3.
Okay, thank you, Jakob. I will share my screen here now. Okay. So do you see my screen now? The right one?
Yes. Yes.
Okay, great. So since Jakob introduced you to the cyber-physical production system, I would like to continue with that. First of all, the first element of the cyber-physical production system is the physical world. And in the physical world, we have the production process and the machines themselves. For the battery cell production process, the first section is the electrode production. You might all know that, but just to introduce that again to you, we have the material first, which we can mix. And then the coating and drying of the electrodes follow, as well as the calendering. For the cell assembly, we have the cutting, stacking, contacting, housing, and electrolyte filling, followed by the formation and aging, as well as the quality control. And in the end, we have the finished cells. The challenges in the battery production are that we have many process steps that I just mentioned. They are very complex and they also depend on each other with all the input parameters and goal criteria, which we have on the left, the input parameters and many requirements and restrictions. On the right, we have the quality criteria, which are very important, of course. And to obtain the best quality, we have to see that there are many influences on the production process. We have different challenges, which are, for example, the combination of continuous and discrete manufacturing. First of all, we have the continuous manufacturing in the very beginning, and in the end, discrete manufacturing. Other influences are, for example, the technical building services. For example, the dry room conditions, which we have for some of the process steps. And this just means that we have many variables and many parameters that influence our process. So it's more difficult to have a fitting quality management system, which is also shown here. We have many different process steps with all the parameters and product properties, and also intermediate product properties, which are shown here. And these are all challenges for the quality management in the end. As for the data acquisition, which is the next step in the cyber-physical production system, we have different goals, especially the economical feasibility, which means we need fitting information and communication technology, which also supports innovative systems. So we also need high temporal and spatial resolution of the data, because all the data we gather is the basis for what we do in the cyber world. And if we don't have sufficient data, we might not have the results we would like to have for the quality in the end. And for the economical feasibility, we also need low costs in data storage and communication. I would like to show you now how we did this in the BLB, what our data acquisition concept is. First of all, we of course have the physical world with the machines and the processes, and the cyber world as well. In the physical world, we have the data acquisition. which can be automated data acquisition or manual data acquisition. Since not all the data can be collected automatically, we also have the manual data acquisition. But for the automated data acquisition, we have the machines that can gather data, and through communication protocols like OPC UA, it can be transferred to the cyber world. In the physical world, the manual data acquisition is also a possibility for data that can't be collected automatically. And for this data, we need someone to type in or to upload the data in any kind to the cyber world. And between those two, we have the tracking and tracing, which is some kind of combination between those two, because we have automatically gathered data and manually acquired data as well, like operational data. And all these data can be combined in the end in a data warehouse in the cyber world. And the data gathered in the data warehouse are the basis for the visual analytics or data mining methods, or any other use you might have for the data. So the key message of this is that we have different data sources, and therefore we need different data acquisition interfaces. The data sources can be very different. For example, the most simple case, I think, is the production machine. And for this, we might have the data access point of a PLC. And the data acquisition interface would then be the communication protocol like OPC UA. But we can also have many other data sources, and therefore also other data acquisition interfaces. And we have to combine all of these to be able to make other statements out of that. Originally, the industrial automation pyramid was used to show the different hierarchy levels in a plant. So the interfaces were between those different levels. But with more complex applications, we now have a CPA-based automation, which means we have many different modules which are linked through different interfaces, and we don't have this hierarchy anymore, or at least not to this extent. For the communication itself, we have different participants or different possible participants of communication. The most simple one is the human-to-human communication through language or body language. Then we have the human-to-machine communication, which might be through different interfaces or simple dashboards, for example, cloud services. The machine-to-machine communication is something like grid computing, and we also have object-to-object communication, like the IoT. And between those kinds of communication, we also have analogies, which are easy to explain with the communication protocol. So the communication protocol is basically just a set of rules to make it easier to communicate between different machines, for example. And it gives a frame for this communication and ensures that all the partners just speak the same language and understand each other. If you imagine two people speaking to each other, that's quite similar. One person says something and the other one replies. It's quite much the same with communication protocols. One asks something or says something and the other one replies. And the protocol defines different things just to ensure that, like I said, both partners understand each other. For example, the syntax is the same. The timing is defined, fragmentation, semantics, and error handling. For example, if one machine doesn't reply anymore, the other partner knows what to do. And one example for these industrial communication protocols is OPC UA, which is a machine-to-machine communication protocol. And like I already mentioned, we have a client-server architecture, which means that we have, like on the right, a client and a server, and the client asks something, and the server replies with the desired information. One advantage of OPC UA is that it's operating system independent, and it works on the upper layers of the OSI model. The OSI model means Open Systems Interconnection, and the upper layers of this are that you can share advanced data, so high levels of abstraction, not just very simple data, and that's a big advantage if you have more complex data. Main features are, for example, that there are integrated security mechanisms and heartbeats. Heartbeat means that the partners check on each other if they are available or not. We have event-based or cyclic updates and other features just like the UTC-based timestamps or quality codes to see if values can be trusted or not. Despite all the advanced protocols that we have to help us communicate, it's just sometimes not possible to acquire data automatically, so that we still have the manual data acquisition. One problem might be that it's just difficult to search through all the data, and some data might also get lost over time or is no longer available if someone loses a notebook or something. And so therefore it's best to have all the data in digital format as well, so that we have large platforms that gather all the data, just like I showed we have in the BLB. But the problem might be that depending on what software you use, you might be tied to a specific manufacturer. That might be a problem, or if different softwares can't communicate. I brought another example from the BLB as well, the data warehouse again. So this is what it looks like. We have different opportunities to use the data here. We can also navigate through the data through different production campaigns, for example. We can look at different production steps or machines, where we can also see the data from the intermediate or final products. And therefore we can compare the different production campaigns, which one looks better. And through this interface, also data upload and download is possible. This is especially important for the manually acquired data. And the whole data warehouse is based on Microsoft IIS. This whole thing again reminds us of the different data sources, since we have the combination of automated and manually acquired data again. Next, I would like to talk about tracking and tracing, which is quite important so that we can see the interrelations between the different process steps and trace back material we used. Traceability is very important for the quality management, and the word traceability itself is the ability to trace the history of application or location of an object, while tracking means the other way around. So we go from the start to the very end with one material, for example. And just to understand the tracking and tracing, we have the different process steps and the different intermediate products resulting in the final product. I hope you can see the laser pointer here. Right, like I said, the process steps, the intermediate product and the final product. And then we might ask, what are the final product properties? And hopefully we can then see and remember which were the conditions of the production. And in the end, we have the initial products, the intermediate products, and at the very end, the final product. This can be visualized through this virtual production information card, a product information card, which we can where we can trace back the materials we used. And the process steps enable us to track and allocate the product data and process data, and the intermediate products help us understand intermediate product features for our quality management. And like I said before, all these products or intermediate products influence each other, and if we are successful with our tracking and tracing and other things we can use, we can trace back the properties and also the interrelations of the intermediate and final products. We have a solution for this in the BLB as well. The tracking and tracing platform, which we can use for production planning, and we can allocate the used material through this tracking and tracing platform through an HMI, human machine interface, at each process and machine. And so we can see the product history and trace it back. Next, I would like to talk about the data storage and management after we have seen how we can gather data and how we can trace products back. We want to store this data and manage it. Therefore, we need to understand what the difference between data storage and data management is. Data storage, first of all, is when we know what type of data we have, where we have it, and how the software or hardware holds, deletes, backs up, and organizes the information. And the data management is more of a practice of constructing this framework we need to store the data and to archive it. For the data storage, we can have different database systems. SQL or no SQL is the main difference. This means that with SQL databases, we have a database that saves in tables. So with one table, we have one type of information. And no SQL means that we can store any data in any document. But the problem with that is that that we might have some problems with the consistency of the data, but it's more flexible than SQL, for example. SQL, therefore, has less errors since we have the tables. For all these different softwares, we have different features with the compatibility, for example, or the speed. Also, the maturity of the different database systems is different. And one example for a platform might be Volkswagen. They combine all the data of the machines and plants they have from their 122 facilities. And over a longer term, they also want to integrate the supply chain as well, so that they can improve their efficiency and also the flexibility of the production. And therefore, they use the digital production platform and an industrial cloud. Next part would be the cyber world and decision support. First of all, I would like to talk about the modeling and simulation. As you can see, we're in the cyber world right now, and for the modeling and simulation, our motivation is to predict the behavior of processes, machines, and production system, as well as factories. And now we could ask ourselves, why are we even modeling and simulating? These are quite recent examples where simulation was used. You can see they all have something in common, that they use simulation or modeling. And the reason for that is that simulation helps us to describe systems that are just too dangerous, expensive, or complex to explore experimentally. And additionally to that, we can also visualize the systems, which might not be possible as well in the real world. The models are essentially approximations of the real world, and simulation describes I would say, practice of emulation of events or systems over time, so that we can gain insights of the behavior, which we can then transfer to the real system. And there are many different benefits besides these the ones I just mentioned. We can also explore processes that just rarely happen in reality, just to understand the dynamics of this in a better way. And we can, of course, plan on basing on our simulation more exactly. We can have new ideas through this simulation. We can visualize and also minimize risks before we invest in something that just wouldn't work for us. The different types of modeling are shown here. First of all, we have the physics-based modeling. Therefore, we just have physical principles and mathematical models that base on these physical principles. The second one is the data-based modeling. For this, we have gathered our data that we just talked about, and the data describe the aspects of the model, for example, via regression analysis. The third one would be the numerical modeling, which is, for example, CFD or CFD or FEM. And therefore, we have the objects which we can decompose into smaller elements. If you think about CFD simulation, for example, we have different simulation cells that are just smaller elements of the bigger one. And then we can look into the specific cells and see what's happening there. One possible application for that would be weather forecast, just to see where it's where you can see it every day, so to say. The fourth one is the Monte Carlo modeling. It's used for different outcomes. So we have a model that and always the same input parameters with different outcomes, and which can be predicted, and therefore Monte Carlo can be used. For example, in the finance sector, but also in engineering, of course. Four other ones are shown here as well. The discrete event modeling, for example, it has something in common with the previously shown ones. We again have small entities that just flow through a system, and actions can be triggered then, and it is similar to the agent-based modeling in that point, for which we have different active agents, right, which are entities again. System dynamics and dynamic systems are other ones as well. For system dynamics, the behavior of a corresponding system is described, and it can be used, for example, in supply chain management. Dynamic systems, on the other hand, is based on mathematical models of dynamic systems, which consist of state variables and equations. These different modeling approaches can be combined, which would be called hybrid modeling. So different modeling paradigms are therefore combined, and it's becoming more and more common practice since the systems we model are getting more complex. Another approach is the multi-level, the multi-scale simulation, which means we can simulate multiple levels, for example, from a process over a workstation to a whole factory. And we can also simulate multiple scales from molecule to material properties, or from seconds to decades, which means over a bigger time frame. And one example I brought today for the mechanistic modeling is the project SimForPro, where we have a process chain model which is connected through structural parameters, or where the process steps are connected through through structural parameters. And we also have a surrogate structural model to model the structure of the electrodes themselves, so that we can link that structure back to the process again. Okay, so now the data analysis and data mining follows, and I would hand that over to Jakob again.
Thank you, Alexandra. So I will share my screen again. So yes, you should see the right screen at the moment. Perfect. So after this introduction into some simulation technologies, ideas, methods, and the brief overview about data acquisition, next we want to talk about the database methods. So how can you use the data with the means of data analytics to gain knowledge about your production facility, and hereby facilitate a better understanding of what actually happens within your environment. We brought one specific use case with us. There are many more, many different other use cases which you can also think about and present. Please feel free again to ask questions after the element data-driven. We can talk a bit more about other use cases as well. Also simulation is definitely, we can answer questions here, but also Professor Franco has a seminar which focused more specific on simulation. So maybe you have attended that seminar or will attend in the future. I will highly advise you, if you're interested in that topic, attend this seminar, since he has a lot of insights into actually simulation methods in depth, because we, from our perspective, look more about on the whole production chain and how to use those methods to gain knowledge about the whole production chain and not only a single process. So with that, we want to start with the data-based models. where you basically try to extract information out of a big database and bring new insights either into the production or into the worker at the production machine, or try to enable a direct feedback loop to the process and try to improve the efficiency of a process, the scrap rate of a process, the energy efficiency. A lot of different technologies, of course, a lot of different goals can be reached here. Also the goal of improving a process and discovering new production clusters can be possible. Yes, perfect. So we will start first with a brief introduction into the terms that are important around data acquisition. Data mining, and data analytics. So when you normally look and try to find papers and ideas and previous knowledge about this topic, you normally firstly stumble up on the term knowledge discovery in databases, KDD process. The KDD process basically describes the process on how to extract information and discover information, knowledge within databases. The process is clustered according to those steps: the selection, pre-processing, transformation, the data mining, and the interpretation and evaluation. You can see here on the right-hand side the different outputs that you can get out of each stage. It's basically a process to follow along to structure your products. We will look on a second process on the next slide as well, which is built upon the KDD process. Within the selection, the target data is selected. So basically, you try to sample your data, look at the data that you want to use, maybe perform the first correlation analysis to see, okay, does the data actually help me or not? In the next step, the pre-processing, you process this data. You try to fill in gaps. So missing data is either excluded or try to include it by the means of statistical analysis or whatever you can think about. And also a normalization of your data normally occurs so that you scale your data within 0 and 1. So you don't have the absolute values, but the normalization of the values. So they are more comparable to each other. In the next step, you transform the data and do factor analysis. And in the step data mining, the actual model is deployed to your data and you try to extract information by the means of different methods within your data. We will talk briefly about different methods that you can use, but we will not give you like the perfect data mining algorithm because there's so many out there. We are not data scientists. We are production engineers and try to use what is out there in our means by improving, by understanding better the production environment with the technologies and use of provided algorithms. The last step is one of the most important steps because data mining is, you can do that, but trying to interpret, to evaluate and actually getting knowledge out of your data is quite important because a lot of data scientists know their stuff quite well when they do data mining, but actually transferring the information back to the worker, the production facility is quite important. And this is the last step. And I want to emphasize that. Always think about how to best transfer your information back to somebody that doesn't understand maybe the data mining process. So with that, we want to briefly give you some definitions so that you can look at these definitions and use the terms correctly, and then we'll jump into some examples. Data mining, as discussed previously, is a part of the KDD process, which identifies or finds patterns in data. So basically use data, try to find patterns in data, explaining towards a specific goal. You normally structure your data mining process in accordance with the CRISP DM process. I think a lot of you have already heard about that process. If not, you can see it here on the right. The KDD is divided into 6 phases, the business understanding. So in the first phase, you normally describe similar to a cyber-physical production system, your actually environment that you want to discuss, which you want to analyze within your data mining project. The next one is the data understanding. So actually making sense of the data that you have, understanding what kind of data you have, what different labels are there, what are the goals maybe in your data. So what are you looking for, aiming for? Is it something like the max capacity within your data when you look at the qualities of the intermediate products and final products in a database? And then the next is the data preparation. Normally, you take up to 80% of your entire time when taking care of data mining processes in those first three steps. The data preparation, data understanding, and business understanding are the core of everything that you perform later. The data preparation takes time because databases are normally not designed for data mining purposes. There are more and more databases out there, and more technologies facilitating that, giving you a better database to fasten up your process. But you will always have to perform basic tasks of data preparation, which includes, of course, filling in missing values, eliminating certain production information because you just don't have enough data, normalizing your data, trying to do some feature engineering to improve the knowledge within your database, or not the knowledge, but the database itself. And then in the next step, you do the actual modeling. Here, of course, there are different technologies, different methods out there. We will see some examples later on. We've talked about the evaluation and the deployment in the last slide as well. It's the actually benefit of the data mining process. So doing all those steps is good, but this is actually the main part. You want to improve a system and hereby deploy that knowledge or bring that knowledge back to your system, your specific environment. The benefits are quite clear. I think most of you know basic benefits of data mining. We've brought an example here. For example, you can think about the customer identification, helping to recognize customers more efficiently. So you have one specific customer coming to you asking for a certain product, and you know that customer quite well. Maybe you can suggest another product to him. So basically what happens with Amazon or other web shops out there, they basically use your profiles and your interests to suggest new information to you. That is, of course, nothing new to you. You all know that, but just as a basic example. When looking towards manufacturing, the benefits are also quite clear, but we brought some examples again here with us. Of course, you can think about optimizing your manufacturing capacities. So optimizing your system itself, trying to improve the output by better bringing knowledge back to the production, but also predicting machine failures. Maybe you've heard of the terms of predictive maintenance. If a certain machine runs in like some certain patterns, it might indicate that this machine maybe needs some maintenance. And if you can predict that more efficiently within your data mining models, you don't need to turn off the machine. You can turn off the machine and fix the machine before the machine actually fails and your production stands still for a longer time normally, because you look towards, well, what was the problem? I don't know. If you have predicted that before within the means of predictive maintenance, you're fixer, you're faster and better to act and improve your production environment. But also you can think about discovering new patterns. Patterns are, of course, towards discovering new process variations, for example, improving your product quality by identifying new clusters, for example. So everything in that means can be there, but a lot of more other benefits are, of course, out there. One benefit which we haven't talked about yet is that data mining compared to simulation. Data mining is normally, or a data-driven model is faster in computing than a simulation. A simulation can run up to like a couple of days. Data-based modeling is normally done within minutes or seconds. The problem with data-based modeling is, of course, your model is only as smart as your data is, because it only knows what is within your data and the data that comes into your model. It can learn, of course, with new data, but describing a process outside your data or a quality outside your data is almost impossible. There are a few approaches that try to do that, but when you try to discover new ways how a machine can actually perform, you need a simulation, and data models are normally not the way to go there. So further with definitions, we've talked about CRISP-DM. Data analytics is a big part of CRISP-DM when we talk about that. Data analytics is the core, has different core elements within it. One of those which you often hear about is artificial intelligence. Artificial intelligence is artificial intelligence enables a computer to think. So it helps a computer to better know, better think, and learn with the data that comes in. It absorbs the data and makes sense out of the data, and can perform different actions. Machine learning is the means of artificial intelligence, AI, deploys statistical methods to learn from data without actually being programmed for that. So you have the next step, artificial intelligence is programmed for a specific case. Machine learning is not specifically programmed for one certain case. It can find its own ways. So the goal of the project is not clearly defined. So this is a big difference, of course. Data science are the methods for understanding and making sense out of data, and it involves a lot of different technologies. So it includes, of course, machine learning, artificial intelligence, but also statistics and visual analytics. So we have the vice versa here, statistics and machine learning. Look it up if you're interested in that later on. I don't want to talk about that. I just want to mention again, once more, neural networks, deep learning. There are also methods within the range of artificial intelligence, machine learning, and can be deployed in data science. When defining data mining, it's important to say that data mining is not all of those and all of those. Data mining employs these methods, these approaches, and is enabled through data science. So when you try to define, when you talk about data mining isn't the same as artificial intelligence, but data mining can use artificial intelligence to gain information about the data that you've discussed or you have seen within your database. So within data mining, there are, of course, different methods, different technologies, different approaches. We clustered them here along descriptive methods and predictive methods. Descriptive, as an example here, you have the clustering of your data. So finding similarities within your data and cluster them in the means of a visualization, or just saying, well, that cluster describes that certain property and that cluster describes the other property. You can see an example here. You have different data points visualized in a normal graph, and you have different clusters that are identified. Technologies for the use of that are k-means. There are a lot of more out there, just some examples here. Predictive is the next step. You don't want to describe only within predictive, you want to predict something. So learning out of your data, predicting an outcome later on. Here, a lot of other technologies can be used, such as regressions, classifications. You've seen that before. If you have worked with that topic, if you have looked at that topic, I don't want to go in detail here. So with that, we have narrowed down the explanation, the definitions, what we understand behind the term data mining, what we understand behind machine learning, what process to follow, and we want to jump into a specific use case to give you some insights what we have done in the recent past with our data that we have in our use case. You've seen a similar process before. We have different kinds of data within a production facility or within a production line of lithium-ion battery cells. You normally start with material as input, and you have information about the material. What kind of material was used, how much material was used, how old is the material, which has also quite big impact. Then you have, of course, the process that transforms this material into a structure or a product. And the process is normally described through process parameters or state variables in our understanding. So how was the machine actually working? how was the setup programmed, how did the process work, and you can of course include sensors here to get better insights into how was the environment around the process. The structure in our understanding is the intermediate product, and it is described by its intermediate product features. So a feature is one specific, let's call it quality of an intermediate product. And the sum of those qualities describe the intermediate product state. So the quality of this intermediate product. And you have the final product. It's the output in the end of your production line after repeating this process structure, and coming to the end with like the final battery cell that is then produced. And this battery cell is of course described by its properties. And these properties can be manifold. You have different properties describing different behaviors of a battery cell. And we normally call them final product properties, FFPs. This can be max capacity, this can be SUH, this can be a lot of different factors. You of course have to decide on what are the main factors you want to focus your project on or your data mining project on to predict or get better insights about that specific use case. What we do is to learn from the intermediate product features and predict outcomes of the final product property. And hereby explaining the process, how do intermediate product features influence the final product? And then going back the step back, if we know that this certain intermediate product feature has a high impact on the final battery cell, understanding how the process that influences that individual intermediate product feature can be improved to improve the overall process. So our approach goes from structure to property to enable us to know property is influenced by a single process, and then improving the process or processes to improve the final product property. What we have done in the recent past is doing a data mining project. We included in our data mining project about 200 cells, Z-folded pouch cells, 15 or 10 compartments, so 15 anodes and cathodes, or 10 anodes and cathodes within a pouch cell. The anode in our use case here, the material is described here, and the cathode here. It was NMC 111 cathode, since the data is a bit older that we used, and the separator used is also described here. We have described before our data acquisition how we achieved actually the gathering of all the information along the process chain. We've seen this picture before, and the map of the battery cell production enabled us to gather all the information of what different intermediate product features you have along the production chain to know what information we need to gather and how that can be summed up in a database to use for our data mining project. Here you can see a simple image of our battery cells, our pouch cells. So first, we stuck, of course, to the CRISP-DM process, which we described, and we performed the basic tasks of data preparation. We started with about 1,000 intermediate product features describing the entire production process. So all the 16 different intermediate products were described by its intermediate product features, and the 16 products brought us 1,029 intermediate product features. Due to some missing values, we limited our data to 155 cells. This was basically the first step, looking at what values were missing, excluding those cells that didn't give us enough information to explain or understand their behavior. In the next step, we performed a recursive feature elimination algorithm based on different models to choose two subsets of 10 intermediate product features. We limited our feature selection here to 10. Just you can of course use other numbers here, but the 10 described a quite good performance for our later model, and including more than 10 features increases of course the computing time, but didn't further improve the model so far. So we could just focus on those 10. Those 10 features here then described the different states of different products and are let's say, the most important intermediate product features along the entire production chain. Yes, so in the next step, we performed a selection operation model Laplace, and also a random forest regression were performed to further prepare and select our data. The model that we built with that data was able to not predict just one final product property, but it was able to predict 3 final product properties at the same time, which is quite good, and I think was novel at that time to the battery cell manufacturing process. We chose to use the final product properties, which you can see here, so the max capacity, the self-discharge, and the SOH after 400 cycles. So we try to optimize or find patterns within our data, aiming towards those 3 final product properties. You can see the performance of the models here below, where the actual battery cells are the green dots, and the lines describe the prediction of the behavior of our model. The performance was then validated through a 5-fold cross-validation, which you can see here, and we got the information that the best model that we can use is the INN, which stands for Artificial Neural Network, and we proceed with that model to perform our different use cases. So this was basically the preparation of the data and the first deployment of the model. In the next step, we thought about, okay, if we have that, we now need to deploy our model into different use cases to actually get some insights out of that model and try to improve either the understanding about the process or either improve the process itself. We have published in the past 3 different use cases, which the first is just the identification of critical parameters and critical influences. So we looked into our data, identified patterns, and gave that patterns or those influencing parameters back to our workers, mentioning, well, this parameter is quite important. Please try to stick within like smaller quality ranges to improve the accuracy or the quality of your final product. We then deployed in the second use case a model-based virtual quality gate. A quality gate is basically a quality management strategy where we divide the entire production chain into single steps, and building a quality gate after each production step, trying to determine the quality of the product, predicting the quality of the later to perceived final product, and then trying to derive any actions from the quality later on. You will see that use case later on. It's quite, I think it was not a good explanation, but with a picture later on, it will be better. In a third use case, in our recent use case, we performed performance-oriented production planning. So we took those information we got from those 2 use cases and re-engineered the entire process, going from, well, now we give different final product properties to our model. We feed them back to our model saying, well, I want to perceive that maximum capacity, that SOH, that this self-discharge within the range, of course, of the data. Please determine for us production clusters of the intermediate product features so that we can explain or determine the quality of the intermediate products that we need to perceive to reach our set goals. All of those use cases are published. So if you are interested in those, look for our publications. You can find them there and get, of course, more insights. I just want to focus today on the model-based virtual quality gate because I think it's quite handy and quite a cool use case and good to explain. So quality gate, I've tried to explain that briefly here again with some pictures. So what you can see here is just the production chain with its influencing parameters described by a production step, an intermediate product, and a later final product. Each intermediate product can be put into context with its quality and the intermediate product state. So the intermediate product quality can be determined within a quality gate. that information, which you can see here just as a sketch, can be used to determine or predict the final product property. And again, here we focused on self-discharge, max capacity, capacity decrease, inner resistance, and OCV. So we can determine within with the intermediate product state the final product property, and we can go along the process, see and determine if the intermediate product, if it changes, how does it actually impact the final product. In the first quality gate, we see we are within our ranges that we set, so within our target value with its ranges. In the second step, we see, well, we are now outside of those values, and we can predict with that the final product property and see that the FFP has shifted. With that, we can, of course, continue our production by either saying, well, it's still okay, I can further produce the same product and still receive a quite good battery cell, or we can adapt the production step in the following step or a step down the line to bring our product back within the desired properties by adapting the target value of a single product. But also, you can of course define, because the production process of battery cells is quite long, quite energy intensive, quite resource intense. If you have produced a bad electrode and you don't want to further produce that, we can of course eliminate that product and just stop the production or further processing of that single product and feed it back either to recycling, and then save energy down the line for the cell assembly and all the dry room condition energy that you need, of course, and then maybe save some money, limit the scrap. We took this process and performed this process with our data along the production. So we took the information, the data that we gathered, and performed simultaneously along the production chain our data-driven quality gates, which you can see here. You can see here the intermediate product features in different states. So first the target, then a predicted final product property for an OK battery cell, and a predicted final product property for an NOK cell. And you will see along the process how those target values shifted and how this information can be feedback to the production engineer, to the worker at the machine. You can see that within the, I wanted to go there, yeah, perfect. We started with the first intermediate product feature, and the second predicted that we stay within the ranges of the desired target values, but you can see here that for an NOK cell, we predicted that we, with intermediate product feature 3, we left the target value. And with that, we left the ranges or had new ranges for the final product properties that were predicted here. And this, of course, has a high influence on the later perceived product, because by losing the track of the good quality and going towards maybe poorer quality, it has an influence on the final battery cell, which you can see on the last slide, that our max capacity was lost or was worse due to a production error that occurred here. And of course, you can see the same behavior in different ways with the SOH and also the self-discharge. This helped us to better understand how we can control the process, or helped us to better get an insight into the product quality, and hereby learn if we need to adapt maybe the production environment, the processes to produce better results. So with that, let us jump back to the presentation. If there are any further questions, we will have in the end maybe a short discussion, or then again, step in contact with us if you want to get any more insights. I just want to briefly talk, really briefly, like a few slides, about decision support and control. So the last element of the cyber-physical production system. I've already shown some works towards that within our data mining use case. So quality management and model-based quality gates, of course, can be also be deployed, as you've seen within the decision support and control element. First, when you talk about decision support and the feedback loop back to the machine, you have to think about, well, how does a human and a machine interact, and compare, of course, a human to a machine, because you will always have the information brought back to the human. The human needs to take this information, that knowledge that is gathered through either the simulation or the data mining or database models, and bring that back to the process and to the machine. And there you can look, of course, machines and humans, they are similar in some kind of ways. We have cognition, that is basically the sensor in a machine. We have sensors and sensors also in the machine, and we have actors, our arms, our fingers, whatever you can think about, and we have also the actors at the machine. So either the gripper or the extrusion unit, whatever you can think about, and we have an interface to communicate with that. And the communication with that interface can be a simple computer, it can be an HMI device, it can be a lot of different stuff, and the interaction between a machine and human is quite important. So giving the human an opportunity to step in contact with the machine and the process, and giving new information to the process, or maybe adapting the process in some ways, is quite important. You can, of course, foster an understanding of what is actually happening by a process monitoring. For that, you can use real-time visualizations, dashboards, monitoring devices. You can, of course, have simple lights on your machine. Is the machine running in according to plan or not? Can you maybe adapt something there? That can be, of course, offline, online. There's a lot of different stuff out there. What we have done within our facility is to implement, in the first step, a dashboard technology on shop floor level, visualizing all different data that we gather, summing up some data, giving some insight specifically into, for example, the energy efficiency or energy transparency within the production processes. And I want to show you quickly how we solved that issue, that problem, within the BLB. So click here. So this is a picture of our BLB Nerve Center dashboard. It's basically a big monitor here, which is within our shop floor, visualizing all the different information that we get from each machine. You have first the layout here showing the different energy consumptions, and then you can see the different machines with their specific process parameters, and also their energy consumption or energy demand, which they currently acquire. You can also do that, of course, on factory scale, not looking at the single process, but also on the process chain and the factory itself, because one of the key driver when looking at energy consumption in battery cell production is, of course, the dry room, with different numbers. It depends on however you want to calculate, but I would say like a rough number, 50 to 40% of your total energy consumption can be linked directly to the dry room. Here, more closer look to our dashboard. It's a web-based dashboard which enables us to visualize different web pages within those different images. We use standard technology for that. It's similar. It's the iframe technology, similar to YouTube, where you have different web servers behind those different iframes, visualizing one certain web server with its visualization. Apart from simple transparency through monitoring, you can, of course, use technologies such as virtual reality or augmented or mixed reality in production environments. You can use a virtual reality tool. You can use virtual reality to test something, to test a new process, to see how you can interact with the process. You can, of course, use it also for education. So if you want to educate your worker or even the student, a virtual reality always helps here. And augmented mixed reality, of course, enables us to interact more directly with the process, since you still see the physical world, but also get like recommendations, as you can see here, about the process. So using AR applications, of course, can help by just looking at the process and seeing within your AR device, if it's maybe your iPhone, if it can be, of course, a HoloLens, it can be pretty much everything. Seeing the certain parameters of that machine, sensors directly without looking at your, of course, computer or HMI, maybe also feeding back information from the cyber world. So having direct feedback from, for example, the model-based quality gates which we have discussed. But also again here, I think if you have visited the seminar of Professor Franco or will in the future, he will take you on a more closer tour towards virtual reality and augmented reality. I just want to briefly mention it here. With that, I will jump into the summary and outlook, and hopefully we have some more interesting questions or discussions. Yeah, since we have a few minutes left, I think. So what you should have learned today is basically a brief overview of our understanding when talking about digitalization. And in our understanding, the core element of digitalization industry 4.0 is the cyber physical production system. The cyber physical production system basically explains each element which you need to take care of when trying to enable complete digitalization within your production facility. Because you have this physical world we have described today to you, how that might look. It's different, of course, at our facilities compared to yours. You need a clear understanding of your facilities. You need a clear structure in your physical world, your physical system. You need a machine. You need, of course, different sensors of the machine. You have the factory. You have to describe all this and learn about this and know from that what you can actually gather what information you can actually gather. We have talked about data acquisition briefly today as well. We gave you some ideas of what the first steps might be, mapping your processes, your intermediate products, your different data sources that you have, summing up the information, how you can actually gather that data. You have seen the table that Alexandra presented. There are also technologies out there, such as SCADA systems. I don't want to mention any names again because I've done that before. There are a lot of more technologies, not just one, but manifold. You can, of course, solve that problem by your own. It's not as complicated as you might think, but of course, it needs a lot of expert knowledge from the automation side, but also from the IT side. We've talked about the cyber world, focusing today on data-driven approaches and simulation approaches. We've given you hopefully some insights on what technologies you can use, what methods you can use, and in a more specific use case explained what the benefit of data-driven approaches can be and what one possible use case is. We have briefly talked about the decision support, so giving you some insights into how to feedback information into a factory system and how that can actually improve the efficiency, if that is your goal, of the production environment. So the learning goals, again, we have the learning goals, cyber world, industry 4.0, CPPS, digital twin, which is basically in our understanding similar or the same, just two different words. We have explained briefly the battery cell production process and its challenges. You all know the battery cell production process and its challenges, so we kept it brief. Learning goals concerning the data acquisition were what different data sources you need to take care of. You have your automated data, you have your manual data. You need to think about how to acquire the one and the other, if you want to acquire the one or the other, or do you just focus on one of those? We've talked about tracking and tracing briefly. Tracking and tracing is quite important when looking at data acquisition. There are a lot of projects out there trying to solve the problem, how to link products with information. And especially, of course, when looking at electrode production, having a specific meter of an electrode that goes into a single cell with its information and its data is complicated, and a lot of work is still being performed here. We've talked about data management and technologies here. Briefly, we've mentioned SQL databases, non-SQL. We've mentioned cloud computing. It's up to you what you want to use, up to you on what technology you actually want to decide. Within the cyber world, we've talked, as I mentioned before, on simulation and data mining. We've presented you a use case from our facility, but there are a lot of more use cases out there, not just from our facility, but also from others. So feel free to look at all the different publications. There's actually a lot of stuff happening within the topic of the cyber world and battery cell production, and that's why it's so exciting. Then the learning goals concerning decision support. That was really brief today, but of course, you need to understand the human-machine interface within the loop of the cyber-physical system. So how does the human actually interact with its environment, and also how you can solve issues towards maybe process monitoring with different methods.